Hi everybody, welcome to lecture 16. Today we're going to be covering implicit differentiation. I'm going to take a moment to explain what it means to have an implicit function versus explicit, so you just know what we're doing here. So sometimes functions cannot be solved in terms of a single variable. Up until now, the functions you've differentiated look something like y equals and then some kind of function and only x. So here's an example of something you've seen before, something like y equals, let's say 17 sine x minus 4x squared. So we would say this is solved for y in terms of x. And this is an explicit solution for y, because the only type of variable you see on the right side is simply x's, and then y is all by itself over here. So this is what it means to have an explicit solution for y. So sometimes you're not able to have a nice solution just like that. However, your function looks more like it has a mixture of different variables. So let's look at this one. This one's going to be y squared plus x cubed minus y cubed plus 5 equals 2y. So if you sat with this for a while and tried to solve for just y using standard algebra techniques that you've learned, you'd have a very hard time solving this for just y. So in this case, we have an implicit formula or function, so implicit formula involving x and y. So what this means loosely is just we have a mixture of x's and y's, and we can't get it to look like nicely like this, where it's y equals just stuff in terms of x on the other side. So this lecture is focusing on how do you take a derivative of something like this. There is a graph of this, and there will be a slope at each point on this graph, but how do you get the derivative of something like this? Well, we're going to learn a new rule. So here's our new differentiation rule for this section. Not rule, it's just one really, one main rule. So if you're trying to take the derivative of a function involving just y's, or some expression involving just y's, that's equal to taking the derivative with respect to y of that function times, and then I'm going to put y prime here. Other ways you may see that notated, which I described in earlier videos, is maybe dy dx, or even f prime of x. But to save myself a lot of writing, usually when I talk about this lecture, I try to stick to y prime when I'm doing this. So what this rule says is you take the derivative of the expression involving y like you normally would, pretending maybe it was just a function of x, and then you tack on a y prime in every spot you had to take a derivative of some expression involving y. Let's go ahead and use this example to practice doing implicit differentiation. So this is going to be our very first example. So we're going to calculate y prime of, and I'm going to just use this example right up here, I'll rewrite it, of y squared plus x cubed minus y cubed plus 5 equals 2y. We're going to find the derivative of this, even though there's a y in many different spots here. So let me show you how this looks. So typically there are the same 5 steps that you're going to follow when you're doing this. Step 1 is to apply d dx to both sides of the equation. So we're going to take the derivative of both sides of the equation. That's what this boils down to. This is take derivative. And this can involve any rules that we've encountered so far and any rules we might learn in the future as well. So we're going to take the derivative of y squared plus x cubed minus y cubed plus 5. And we'll take the derivative of the right side as well, which is going to be 2y. So Anytime I encounter some kind of expression involving y's, I'll take the derivative pretending it's an expression with x's and then tack on this y prime here. This is the new rule. Okay, so y squared, that involves y's. So let's take the derivative normally with the power rule. It'd be 2y. Because I took the derivative involving something that had y's in it, I need to put y prime here. Okay, moving on. I take the derivative of x cubed. That just has x's in it. So that's just a normal power rule, how we're used to doing it. So the derivative of this is 3x squared minus. This expression involves y's, so I need to remember a y prime for this one. So derivative of y cubed is going to be 3y squared, and then tack on that y prime. Derivative of 5 is just a constant. It doesn't involve y's. So that's just going to be 0 equals. This one involves y's. Derivative of 2y would be 2, and then I have a y prime as well. So once you have this, the next step generally is get all terms involving y prime on one side of the equation. So that's generally my second step. So I'll move everything to the left side. You'll see that 2y prime is already there waiting for me. I also have this minus 3y squared y prime, so that involves a y prime. I need to move this one over with the other ones. So if I move this over, I'm going to subtract 2y prime. That equals, and I'll move everything that doesn't have a y prime to the right side. So the only one I see is this right here. And if I move it over, it's minus 3x squared. And I think I'm good there. So once you've done this, you're going to factor y prime. I'll just, that sounded like I was going to say something else, but just factor y prime. So from this side where I have all the y primes, so factor that out, and you get y prime. And what's left is 2y minus, what's left here is 3y squared. And here I have a minus 2 equals negative 3x squared. And then as long as I make sure this doesn't equal 0, so just got to be careful of that, but we're going to divide to solve for y prime. So y prime times this, I can divide this whole factor to the right side to solve. So y prime is going to be negative 3x squared over 2y minus 3y squared minus 2. So this is kind of the standard routine you follow. A lot of the problems that you see for implicit differentiation look like this format. Your answer looks like a giant fraction if you have a very complicated problem. Okay, so this is the derivative. So this gives you the slope. So this is the slope of the original function. So that function was over here, right here. I'm not going to say function. I'm going to say the original graph. Who knows if it's a function right now just by looking at it, but I'm going to say the original graph. All right, let's try another example. So this time I won't write out every single step in words, but I'm going to show you all the steps for this next example. So example here is going to be, I'm going to calculate dy dx if sine of y plus x cubed y squared minus cosine of x equals 2y. OK, so same steps apply. It says calculate dy dx, but again, I just know this to be y prime. It saves me ink to just write y prime, so I'm just going to do that instead. There are a couple more rules involved in this one than the other one. So here I'm going to take the derivative of sine. This is going to be cosine of y. And this was an expression involving y's, so I need to also tack on y prime based on this new rule I learned. This requires the product rule. So let's go through that. I'll put a giant bracket. Here we're going to take the derivative of the first, which is 3x squared. That didn't involve a y, so I don't need a y prime there. And then I didn't do anything to this y squared, so I'm going to leave it. Plus, I'll leave this one alone now, x cubed. Now I'm taking the derivative of the second one. That requires a y prime because I'm taking the derivative of something that involves y. So this will be 2y, and then don't forget that y prime, because in that step of the product rule, you actually took a derivative of something involving y's. Moving along, I have the derivative of cosine is minus sine, but I have a minus in front of this already. So this is plus sine x equals, and then this side would be 2y prime, because I took the derivative of 2y, had a y prime. Okay, now I'm going to gather everything on one side. So it looks like I have cosine y prime. This term, this third one, also involves y prime. So this is 2y x cubed y prime equals, oh, I've almost forgotten one of them. Do you see it over here? This one right here on the right side, I'm going to subtract it over, and I'll get minus 2y prime equals. Everything that doesn't involve y prime is going to go on the right side. So there's this one right here. So minus 3x squared y squared. And then this one also didn't involve y prime, so this is going to be minus sine x. All right, so you're going to factor out that y prime, and you're going to get cosine y plus 2yx cubed minus 2 equals the right side. You don't mess with this side at all. And then finally, you'll take this final factor and divide it over. So y prime is going to be negative 3x squared y squared minus sine of x all over cosine of y plus 2yx cubed minus 2. And this is my derivative. So you can see the process is pretty standard for finding these derivatives. It's just how complicated is the thing that you're starting with going to be? Because that's where the difficulty might come in, is trying to find the derivative of something very complicated at the very start. Okay, so I'm going to pause here for a moment, and I'm going to do some more examples with you in just a second. Okay, so I'll see you soon. Okay, so I have a number of examples up on the board here. If you want, you can try them out yourself to check your understanding and see how far you get. I'm going to go ahead and start with the first one now. So this says use implicit differentiation to find the equation of the tangent line to xy cubed plus xy equals 14 at the specific point 7,1. So it's a very standard question to ask for the equation of the tangent line on exam 2. This is just another application of that using a new rule, the implicit differentiation rule. The equation itself is not so bad to take the derivative of. So we're going to take the derivative of the left side, which is xy cubed plus xy, and we'll take the derivative of the right side, which is just 14. So these both require the product rule. So the first one's going to be derivative of x is 1 times y cubed plus, I'm going to leave x alone, and the derivative of y cubed is 3y squared, but I need to tack on y prime because that involves a y in it, what I just took the derivative of. That finishes up the product rule. Now I'll do another one with xy. So this is going to be 1y, then plus, I'll leave x alone, and the derivative of y is y prime. And then the right side is just equal to 0. So the derivative of a constant is just 0. Now I'm going to go ahead and do the typical steps. So I'm going to solve this for y prime. So here I have 3y squared xy prime plus xy prime. So those are all the terms I see with y prime in it. And I'm going to move over the other two terms. So I'm going to move over the y cubed and the y. So they're both going to become negative if I move them to the right side. Now I'm going to factor out the y prime that's in common here, and I get 3y squared y, or sorry, 3y squared x plus x equals negative y cubed minus y. And I'll finally divide over by this factor here. So y prime is going to equal negative y cubed minus y over, and I get 3y squared x plus x. So this is the slope of the tangent line anywhere on this original graph. Specifically, I'm looking for the slope at 7,1. To find the slope of all the other equations we've done so far, you just have to plug in x, But the difference here is now you have x's and y's that are both involved in the slope equation. So let's plug in 7 for x and 1 for a y. So everywhere I see a y, I'm going to plug in a 1. So that means I get negative 1 cubed minus 1 over 3 times 1 times 7 plus 7. So on top here, I get negative 2. And on the bottom, I get 3 times 7 is 21, plus 7 more is 28. So my slope is going to be negative 1/14, or sorry, negative 1/14, that was right. And I have a point here. So let's use my point slope form. I have y minus y1 is 1 equals m, which is negative 1/14, x minus x1, which is 7. You can rearrange that in any order you like, but this is going to be the equation of my tangent line. OK, moving on to the second example. It says for which x values is the slope negative 1 for this equation right here. So now they're giving me a specific slope. So what this means is that y prime is going to equal negative 1. That's what they're telling us. The slope is going to be negative 1. We're still going to start the same way. I'm going to take the derivative of x squared y squared plus xy, and then the derivative of the right side, which is going to be 2. Both of these require the product rule again. So here I'm going to do 2x leave y squared alone plus leave x squared alone. Derivative of y squared is 2y, and then I need a y prime. Here's the product rule we just encountered right up here. So the product rule for this was y plus xy prime. You will be seeing that a lot in this section, so you might actually just memorize that that's what it is. And the derivative of 2 is just 0. It's a constant. Now, instead of going ahead and doing the other steps to solve for y prime, let's just be a little more clever about this and use our information. So we know y prime ahead of time. We know that it's negative 1. So in the 2 spots I see here where y prime is, I'm going to just put negative 1 in. So this will be 2xy squared. This y prime right here is negative 1, so I'm going to get negative 2yx squared plus y minus x, because I plugged in a negative 1 here for y prime. And now I see 4 different terms here. I'm going to attempt factor by grouping. That's a good signal. If you have 4 different terms, factor by grouping might help out. So for the first group here, I have 2xy in common, and you get x minus y left over. I already have x minus y here, so if I just factor out a 1, I don't mess with anything. So I just want to factor out 1 so that these two things match. And this gives us a factoring of 2xy plus 1 times y minus x is 0. So there's 2 things that could be going on. Either 2xy plus 1 could be 0, or we could have y minus x could be 0. This will give us 2 different possibilities. So either y could equal negative 1 over 2x, where all of 2x is in the denominator. So I got that from rearranging the first one. And the second one's easier to rearrange. It's just y equals x, if I add the x over. So these are the 2 situations where you get negative 1 for the slope of the original. However, if I plug these into the original, maybe I can narrow down even further and find these x values. So let's plug these in one at a time. So first thing I'm going to do is separate these a little bit just to give us some more room. So here's my 2 situations. Let's plug this back into the original and see if we can figure out what's going on. So we're going to plug this into the original here. So I get x squared. Instead of this y squared, I'm going to plug in negative 1 over 2x and square it, plus x. I'm going to plug in, for y, I'll plug in negative 1 over 2, x. I'm not going to write the equals 2 right now. I'm just going to see what this is going to be. So if you notice what happens here is I get an x squared cancels with x squared. Negative 1/2 squared is 1/4. Here my 2x's cancel, and I get, let me see here, I get minus 1/2. So then 1/4 minus 1/2 is minus 1/4. But that's certainly not equal to 2, which is what I'm supposed to get on the right side, right? So if this is impossible, I would just say no solution, no real solution. So this situation is just impossible to happen based on the restriction I have here for this equation. Let's see if we can get anything for this one. So for all the y's, I'm going to plug in x. So I'm going to get x squared. Here I'm going to get another x squared. Plus, here I have x, and instead of this y, I'll plug in x equals 2. Already, this is a good sign because my x's aren't canceling out. Here, x squared times x squared is x to the 4th plus x squared. Instead of saying equals 2, I'm going to subtract it over. So it's going to be minus 2 equals 0. And this can be thought of like as a standard factoring problem because this power here is double this power. So I'm going to try my standard trinomial factoring. So x squared times x squared gets you this x 4th. And how am I going to get a minus 2 and a plus 1 here? Well, I'm going to do plus 2 minus 1. So these multiply to negative 2, and then they add up to the positive one I need. So either x squared plus 2 is 0, or we could have this, x squared minus 1 is 0. Well, this one you'll see is impossible, because this tells me x squared is negative 2, and I can't have the square of a real number be a negative number. So this one is also no solution. So that leaves us with just this. And will we get solutions here? Yes, we will get 2 of them. So this is going to be x squared equals 1. And if I square root both sides, I get x equals plus or minus 1. So these are the 2 x values that we were looking for here, where the slope is negative 1. OK, this last example here, it's very similar to this. They just want you to find, for this equation, the vertical and horizontal tangents. So they are giving you a specific slope, just like this one. These are 2 very special examples that you'll need to know. So when you have a horizontal line, or horizontal tangent line, the slope is 0. So that's what it's telling you. And then for this one, it's saying for a vertical line, the slope is undefined. OK, so that's how you interpret those. Now let's go ahead and take the derivative of this equation right here, just to get us started. So I have d dx of x squared plus y squared minus 2x minus 4y equals the derivative of the right side, which is negative 1. Luckily, this doesn't involve the product rule, so this is simpler than that other one over there. Derivative of x squared is 2x. Derivative of y squared is 2yy prime. Derivative of 2x is minus 2. And the derivative of 4y is just 4, but then tack on the y prime. That equals 0. I'm going to go ahead and solve this one for y prime, like I did over here. So this is 2yy prime minus 4y prime equals, I'm going to move the move the 2x over and move the 2 over. I see every single term has a 2, so let's divide it out. I get y prime minus 2y prime equals negative x plus 1. So every single term had a 2, so I divided that out. If I factor out the y prime, I get y prime y minus 2 equals negative x plus 1. And this tells me that y prime is negative x plus 1 over y minus 2. So we have 2 things to do here. So the first one that I'm going to do is I want a horizontal tangent. So remember, that means that the slope is 0. And this right here is my slope. So negative x plus 1 over y minus 2 equals 0. Well, that's 0 over 1. And the way you're going to get any fraction like this to equal 0 is the numerator needs to be 0. We need this to be 0. I don't care what this is going to be. As long as it's not 2, this will be defined. So I'd like to set the numerator equal to 0 in order to find the horizontal tangents. So the idea is you set the numerator equal to 0. So this is a quick solve. This is going to be x equals 1. Now we don't get off that easy because it says, where does the circle have vertical and horizontal tangents? Well, this is the x-coordinate, but that doesn't describe completely where it is. So I know it's going to be at x equals 1, but I'm going to get the y value as well. So let's go back to the original to do that. So I'm going to plug in 1 for all of the x's up here, and I'm going to get 1 squared plus y squared minus 2 minus 4y equals negative 1. So what we're doing is we're plugging in. So I'm going to plug in. I messed that up. Let me write that again. So I'm going to plug in x equals 1. And what we got was 1 plus y squared minus 2 minus 4y equals negative 1. So just plug it back into the original. So if I do that, I get y squared minus 4y. Here I get 1 minus 2 is negative 1. And I have a negative 1 on the right side. So all the constants cancel, and I get this. And if I factor out y, I get y minus 4 equals 0. So there's 2 possible y values. So y could be 0, and y could be 4. So actually, I have 2 different spots. It's these 2 spots where we have a horizontal tangent. OK, so that's half of it. Now we want the vertical tangent lines. And this is where the slope is undefined. So how am I going to make this slope undefined? So let's start doing that here. So this is the vertical tangents. We need y prime to be undefined. So what that means for this is, how am I going to make this undefined? It means I need to set the denominator equal to 0. So that's the idea. That's how I make this fraction undefined. So that means y minus 2 should be 0, or y is 2. OK, so I'm anticipating there are going to be 2 points where this occurs as well. And why is that? It's because of the type of equation we're dealing with, right? We have a circle. So if you have a circle, I'm not going to give myself an xy plane like that. I'm just going to draw a circle. So we found 2 horizontal tangents, and we're looking for 2 vertical tangents. So it's going to be the left and the right most points of the circle. Those are the vertical tangents, and then we found the horizontal tangents already. So it's just because we have a circle, that's how I'm anticipating there's going to be 2 of these as well. So we know y equals 2 makes us undefined. Let's find out what x value that was. So if I go back to the original, so I'll plug in y equals 2. I get x squared plus 4 minus 2x minus 8 equals negative 1. So that's plugging in y equals 2 to the original. Then I'm going to solve this. I get x squared minus 2x. 4 and negative 8 make negative 4. And then I'm going to add 1 more over. So I'll get negative 3 equals 0. And factoring this, I get an x minus 3x plus 1 is 0. So I have 2 different values. X could be 3 and x could be negative 1. So filling these in, I have these 2 points where we have vertical tangents. And now I can complete the picture here. So my horizontal tangents were at 1, 0 and 1, 4. And my vertical tangents were at, I'll put it over here, 3, 2 and negative 1, 2. And look how this all makes sense. Here's the center of the circle. So these should be level, and these should be level. The circle is symmetric. So you can tell by my picture that the radius of this circle should be 2. OK, so that's a very standard process for finding vertical and horizontal tangent lines. It's either you set the numerator or denominator 0 of the slope. All right, we're going to see just a few more applications in the next part of this video. So I'll see you very soon. So now what we're going to do is learn a few more derivative rules with the help of implicit differentiation. So these are going to be new derivative rules. And the first one we're going to talk about is the derivative of sine inverse of x. So what we're going to do is we're going to use implicit differentiation to help us get there, now that we can differentiate equations involving more than one variable. So what I'm going to do is I'm going to say let y equal sine inverse of x. So let it equal that function. Then if I apply sine to both sides, so if I say sine of y equals sine of inverse of x, what I'm saying is sine of y equals, and then sine and sine inverse cancel, and I get just x. So we have this. However, I can take the derivative of both sides with respect to x, so I have d dx of sine y equals the derivative over here of x. This one right here, I know the derivative of sine, it's just cosine y. And then I use my chain rule, so the inside here has y. Derivative of y is y prime. Okay, and then this equals, derivative of x is just 1. Now if I solve, I get y prime is equal to 1 over cosine of y, and we know this function to just be secant of y. So y prime is the derivative of y, which is sine inverse. So if we can figure out what this is, then we know the derivative of sine inverse of x. I'm going to draw a triangle. So my angle here is going to be y. And I know that sine of y is x over 1. Sine is opposite over hypotenuse. So I have opposite over hypotenuse. If you use the Pythagorean theorem, you'll see that the other side is 1 minus x squared under the square root. And then secant is 1 over cosine. And because cosine is adjacent over hypotenuse, this is hypotenuse over adjacent. So secant of this angle here is hypotenuse 1 over adjacent, which is the square root of 1 minus x squared. So I can fill that in. My derivative, y prime, is equal to 1 over the square root of 1 minus x squared. So that's pretty cool that we can use implicit differentiation now to get the derivative of some other functions that we might not know the derivative of. So what I encourage you to do is you should try things like cosine inverse of x or tangent inverse of x. The other trig functions have inverse functions as well. So maybe you want to try that on your own. When you're done using this method, see if you actually found the correct answer by looking it up. Let's look at another one. So how about the derivative of ln of x? So this is something we haven't talked about yet, is the derivative of ln of x. Let's let y equal ln of x. So this is what we want to find the derivative of, just like I wanted to find the derivative of sine inverse of x. If I use e, I'll have e to the y equals x, so just exponentiating. So now what I'm going to do is I'm going to use implicit differentiation to take the derivative here. So I'm going to have d dx of e to the y equals d dx of x. The derivative of e to something is itself. Using the chain rule, though, I have the derivative of the power, which is y prime. And then this is 1, so then this means that y prime equals 1 over e to the y. However, e to the y is x. So this gives us that the derivative of ln of x is 1 over x using implicit differentiation. So again, a very cool application of this to show this rule that we technically didn't have yet. You might remember it from high school, but we didn't have that yet until now. So that's good to know. I want to look at one more thing. So we're going to look at an important limit. So the limit I'm going to look at is the limit as x goes to infinity of 1 plus 1 over x to the x. We're going to show what this equals. So what I'm going to do is I'm going to let f of x be ln of x. So this is the function we just took the derivative of. So I'm going to use a piece of information over here to help me with this limit. So first I'm going to start with the fact that f of x is going to be ln of x. I'm just going to let that be that. I know the derivative of ln of x is 1 over x. So therefore, f prime of 1, if I plug in 1 to this, it's going to be 1. However, I also have the limit definition of the derivative. So I know that 1 equals f prime at 1, which is the limit as h goes to 0 of f of 1 plus h minus f of 1 over h. You're all probably screaming at me right now because I brought back this thing from the depths of exam 1 material, but it's just to using this to prove this important rule. Let's keep going here. So I have the limit as h goes to 0. F of 1 plus h, I would plug 1 plus h into f, if you recall how we do that from the old material. So this is log of 1 plus h. And then log of 1, any base. Log any base of 1 is just 0. So I don't need that. And this is all over h. So now what I can do from here is I can say, well, 1 is equal to the limit as h goes to 0, ln of 1 plus h over h. I'm going to use log properties here. So this is equal to the limit as h goes to 0. This is 1 over h times ln of 1 plus h. What can you do with something in front of log? What's the property? Is you bring this up to the power. So this is the limit as h goes to 0 of log of 1 plus h to the 1h, 1 over h. OK, so now what I'm going to do is I'm going to say, because 1 equals that, I'm going to raise both sides using base e. So I'm going to use e to exponentiate. So I get e to the 1, which is equal to just e. The e here cancels with ln, and I get the limit as h goes to 0. And e cancels ln, and I get 1 plus h to the 1 over h. OK, now I'm going to make a substitution. So we're going to let h be equal to 1 over x, just so I can get the form of the limit that I'm looking for up here. So if you rearrange this, you would see that x is equal to 1 over h. And now let's go ahead and make that substitution. So we have the limit. I'll look at this in just a second, but it's going to be in terms of x now. Here I have 1 plus h is equal to 1 over x. And again, h is equal to 1 over x here. So I have 1 divided by 1 over x. It's just x. And what will x go to? Well, if h is going to 0, I have 1 over something going to 0. We've said the rule for this is a constant over 0, or a number going very close to 0, is going to go to infinity. So here I'm going to choose positive infinity. So you'll see now that I have exactly what I need. The limit as x goes to infinity of this expression is equal to e. And this is a very important limit that you'll see come up very often. So here's another application. Now that I know what the derivative of log is, I could use that to prove this important limit. All right, I think that about wraps things up. Go ahead and try your quiz, and I will see you in the next video. Send me any questions you have by email, and have a nice day. Bye.